Imagine trying to navigate a flight from New York to Tokyo, but the only tool you have is a massive stack of flat, local city street maps.
Yeah, that's not going to end well.
Right. I mean, you can tape them all together, but eventually the geometry just breaks down. The math fails. And today on AI Paper Podcasts, we are looking at a paper that proves AI researchers have been making this exact same geometric error inside neural networks.
It's a huge issue, yeah.
The paper is called Do Sparse Autoencoders Capture Concept Manifolds by Usha Bala, Thomas Phil, and their colleagues. And let's jump straight into the 1-minute summary for you.
Let's do it.
So for years, AI interpretability has relied heavily on the linear representation hypothesis, or LRH. This is basically the assumption that neural nets represent concepts as independent straight-line directions in their activation space.
Right, and sparse autoencoders, or SAEs, which are, the current state of the art for understanding models, they're built entirely on this linear assumption.
Exactly. But this paper proves empirically that concepts actually form low-dimensional, continuously curved manifolds. And the researchers reveal that current SAEs fundamentally fail to capture these curved geometries.
Because of their architecture, yeah. They fall into this dilution regime.
Right. They fragment these continuous manifolds into redundant, overlapping features with mixed selectivity. It's a mess.
A total mess.
So to solve this fragmented mess, the authors introduce a post hoc, unsupervised method borrowing the Ising model from statistical physics.
Which is such a cool approach. By looking at anti-correlated activation states, they can group those fragments back into coherent structures.
Exactly. And ultimately, the paper argues that the future of interpretability has to treat geometric objects, not just straight directions, as the fundamental units of computation.
And, the implications here really challenge the entire foundation of how we currently debug and interpret large language models. Well, the interpretability community has essentially bet the house on finding individual linear features that cleanly map to human concepts. But if the underlying data structure is naturally curved, forcing a linear projection onto it creates a massive blind spot.
Producing artifacts that we...
Yeah, artifacts that we might mistake for the model's actual reasoning process.
Wow. Okay, so that sets up our core mission for this deep dive. We need to unpack the mathematical reality of how these models actually store information, why our current tools are creating these artifacts, and, what ML engineers need to do to fix it.
Yeah, it's a critical shift in perspective.
So let's start with the dominant paradigm, right? The linear representation hypothesis. Under LRH, we assume that if you want to locate the concept of, say, a golden retriever in the residual stream, you are just looking for a specific vector.
Right. You assume the representation is just this additive mixture of directions, the vector for dog plus the vector for yellow plus fluffy.
Right. Why is that assumption so popular?
Well, it's computationally very convenient to assume a linear algebraic structure. It allows us to use standard tools like linear probes to find concepts.
Oh, sure.
We assume that the activation space is in superposition, meaning the model is packing more concepts into the space than there are dimensions. But we still assume all those concepts are fundamentally straight lines.
And an SAE is explicitly designed for that, right? To take that dense, tangled space and project it into a higher dimensional space where those linear directions are disentangled.
Exactly, disentangled into sparse orthogonal features. That's the goal.
But then this team actually looks at the empirical evidence. They analyze the intermediate layer activations of Llama 3.18b.
Yeah, a real massive model.
And when they project these high-dimensional activations down using dimensionality reduction tools like PCA, just to visualize the variance, the concepts do not look like independent orthogonal spikes.
Not at all. They exhibit these continuous, really smooth geometric structures.
Like curves.
Yeah, curves, loops, spirals, and the variety of concepts forming these shapes is just striking. They tracked the concept of age, capturing tokens that range from young to elderly.
Oh, wow.
They tracked temperature, mapping the transition from freezing to burning. They looked at days of the week, color hues. In every single case, the reduction revealed continuously curved surfaces.
So the model isn't storing freezing as some binary switch that gets flipped on or off.
Right, exactly. It is mapping freezing as a specific coordinate on a continuous temperature topography.
That is fascinating. And they also proved that this geometry is causally linked to how the model actually generates text, didn't they?
Yeah, they performed steering interventions right between the centroids of these concepts.
So if you isolate the activation vector representing Wednesday, And you mathematically interpolate it along that curved manifold toward the vector for Thursday.
The token probabilities for the model's output shift in a perfectly smooth correspondence. It's wild. The model is literally sliding its internal state along that curve to adjust its predictions.
Okay, but what happens if you try to steer along a straight line instead? Because that's what LRH says we should do.
Steering along a straight line yields completely different results in high-dimensional space. If the model relies on the distance and curvature along a manifold to encode those continuous relationships, a straight line intervention might pull the model off the manifold entirely.
Always.
You end up in a region of activation space that the model has never even seen during training, which, often leads to gibberish or totally hallucinated outputs.
And I want to note here, for you listening, the authors also identified political bias as one of these continuous manifolds. The model essentially maps out different ideologies spatially.
Yeah, it does.
And obviously we are strictly reporting the geometric structures the authors found here without endorsing or analyzing the political viewpoints themselves. But the key takeaway is that the model organizes these complex, abstract human ideologies as a continuous landscape, rather than discrete categories.
Right, it's not a binary left or right bucket, it's a topography, which forces us to evaluate the tools we use to survey that landscape.
Right.
If an engineer is using an SAE to find a feature that controls political bias or temperature, they are essentially taking a straight edge to a curved surface.
Let me play devil's advocate for a moment, though. Putting myself in the shoes of an ML engineer actively using SAEs to debug a production model.
Sure, go for it.
If LRH is technically flawed and concepts are curves, why are SAEs still working so well in practice? I mean, people use them at scale to steer models safely. Researchers use them to find candidate biomarkers in genomic models.
That's a fair point.
If a straight line is a good enough local approximation of a curve, why does the global geometry matter? Going back to my map analogy from the intro, a flat map of Manhattan works perfectly fine if I'm just trying to find a coffee shop. I don't need a globe for that.
No. A flat map works if you only care about a highly localized area, and an individual SAE feature acts exactly like a localized map. If your only goal is to find an activation that spikes when the model processes the word freezing, an SAE will likely find a feature for that. You've solved your immediate local debugging problem. But the limitation becomes apparent when you try to understand the model's underlying logic or perform systematic interventions.
Because I don't know how freezing relates to anything else in the network.
Exactly. You miss the global structure entirely. You miss the fact that freezing is intimately connected to cold and warm and hot along a shared dimensional axis.
Wow.
More importantly, because you forced a linear projection onto a curved space, that feature you found for freezing is almost certainly capturing spurious correlations.
So it might also fire when the model processes something completely unrelated.
Yes, just because that unrelated concept happens to lie along the same straight line trajectory in the broader 128-dimensional space.
Oh, that's a huge problem. Let's formalize how this breaks down. The authors developed this theoretical framework to evaluate how a linear tool could theoretically map a curved space, right? While maintaining the constraints of an SAE.
Right, and an SAE really has two competing constraints. It has to accurately reconstruct the original activation, keeping the mean squared error low.
That's the first one.
Yeah, but it has to do so using an L1 penalty, meaning it must use as few active features or atoms as possible. It has to be sparse.
Right, those two constraints define the optimization landscape. And the authors established two theoretical ideals for how an SAE could solve this problem. The first ideal scenario is compact capture.
Yes. In this regime, the SAE allocates a small, dedicated group of atoms whose linear span entirely contains the manifold.
So let's visualize this for you. If the underlying concept manifold is a 3D sphere embedded in a much larger space, compact capture means the SAE successfully discovers the overarching X, Y, and Z axes of that specific sphere.
Which is an elegant global solution.
Right. With just those three global variables, you can accurately reconstruct any point on the surface of the sphere.
It perfectly captures the intrinsic dimensionality of the object. But there is a second ideal scenario, which they call shattering or tiling.
And this is purely local, right?
Purely local. Instead of finding the global axes, the SAE distributes the manifold across a large number of highly selective features that each tile a tiny restricted region of the geometry.
Sticking with the sphere analogy, tiling is like covering the entire surface of the sphere with thousands of tiny, flat Post-it notes.
That's a great way to picture it.
So each Post-it note is a single SAE feature. It only fires when the activation lands on that exact specific patch of the sphere's surface. It's incredibly sparse because for any given point on the sphere, only one Post-it note is active.
Right. And both compact capture and perfect tiling can theoretically satisfy the SAE's objective function. They both yield low reconstruction error, and they both maintain sparsity.
Okay, so the critical question for the interpretability community is, when we train an SAE on a real neural network, which of these two ideal scenarios does it actually pull off?
And to answer that, the authors built a highly controlled synthetic benchmark. Because real LLM activations are noisy, you know, and we don't know the ground truth of their geometry.
Right.
So they constructed 8 mathematically known manifold types. They built perfect circles, spheres, tori, Mobius strips, Swiss rolls, and flat disks.
And they embedded these perfect geometric objects into a 128-dimensional space to simulate a network's latent representations.
Exactly. Training an SAE on this synthetic data allows us to see exactly how the architecture behaves when forced to reconstruct a known topology.
So what did they find?
Well, they swept the sparsity parameter, often denoted as the L1 coefficient. They systematically varied how aggressively the SAE is penalized for using too many features. And the empirical results show that real SAEs almost never achieve compact capture. They just fail to find those clean global axes.
And I'm guessing they don't find the perfect Post-it note tiling either.
Nope. Instead, the SAEs get trapped in what the authors call the dilution regime.
The dilution regime. We need to explain the mechanics of this dilution, because this is where the current state-of-the-art tools are actively failing.
Yeah, the dilution regime is a worst-case hybrid of the two ideals. When you apply the sparsity penalty, true global features like those X, Y, and Z axes, they're penalized because they have to activate constantly to reconstruct every point on the manifold.
Oh, and that violates the sparsity constraint.
Right. But the SAE also has a limited dictionary size, meaning it doesn't have enough capacity to create a perfect, non-overlapping Post-it note for every possible point.
So it's basically squeezed from both sides. It can't be global, but it doesn't have the resources to be perfectly local.
Exactly. The optimization process settles into this messy compromise. The geometry is diluted across a larger, partially redundant set of features. Individual SAE atoms lose their specificity.
So you end up with a fragmented mosaic of features that are highly redundant and just locally sloppy.
Yeah, perfectly said.
It's like asking someone to tile a bathroom floor. But instead of using perfectly cut ceramic squares, they just scatter a bunch of irregularly shaped overlapping bath mats.
That is exactly what it's like.
And some of those bath mats stretch out into the hallway. And that stretching is what the authors call mixed selectivity, right? Because the feature is forced to cover too much irregular space. It starts firing for the concept you care about, but it also fires for completely unrelated noise in that 128-dimensional space.
And mixed selectivity is the absolute bane of interpretability. If an atom fires for a specific point on the temperature manifold, but also fires when the model processes a specific syntactic structure, you can no longer trust that atom as a clean proxy for temperature.
Wow.
The most alarming takeaway for researchers here is that an SAE can achieve a phenomenally low reconstruction error while being completely trapped in this dilution regime.
Because the SAE loss function is fundamentally blind to geometry. It only cares about placing the data point back as close as possible to its original coordinates.
Right. It will happily use a redundant, diluted, mixed selectivity set of features to achieve that low error, completely ignoring the topology of the underlying concept.
So relying purely on reconstruction error to validate an SAE is super misleading.
Very misleading. If researchers try to interpret model behavior by analyzing those diluted features in isolation, they are just looking at localized noise. They are staring at a single overlapping bath mat and trying to infer the architecture of the entire house.
Okay, this presents a massive engineering roadblock. If our best featurizers are fragmenting these continuous manifolds into a diluted, uninterpretable mess, how do researchers piece the true geometry back together?
Well, the authors don't just point out the flaw. They propose a really clever post hoc, unsupervised discovery method. And to do it, they borrow from statistical physics.
Right, because standard techniques like measuring the cosine similarity between the feature vectors fail miserably here.
They do. Because the features have mixed selectivity, their vectors are polluted. Two features might point in similar directions for completely spurious reasons, leading to false positives if you just rely on angle distances.
So instead, they use the Ising model. We're basically using a magnetic physics equation to find the structural alignment of fragmented AI concepts, which is mind-blowing.
It really is. Historically, the Ising model is a mathematical model of ferromagnetism in statistical mechanics. It describes how the magnetic spins of atomic particles align with each other.
And they applied this exact physical framework to the binary activation states of the SAE features. They look at the entire population of features and treat them as either being spin up when active or spin down when inactive.
Exactly. And by modeling the joint activation statistics across the data set, they construct a pairwise coupling matrix.
So they aren't simply looking for features that frequently fire together.
No, they are learning the structural co-activations and mutual exclusions across the entire dictionary. The Ising Hamiltonian captures the energy of the system, identifying parameters that describe how strongly one feature's activation forces another feature to turn on, or crucially, forces another feature to stay off.
And that anti-correlation mechanism is the secret to reconstructing the geometry, isn't it?
It is the secret sauce.
If you have a continuous manifold for temperature, and one SAE fragment fires for the freezing region, a different fragment that fires for the burning region should practically never be active at the same time.
Right, and the Ising model captures that repelling force. The negative coupling tells the algorithm that these two distinct fragments are opposing boundaries of the same underlying topological structure.
So the anti-correlation literally carves out the shape. The model infers the geometry by mapping the constraints of what cannot happen simultaneously.
Yes. And applying this to the Llama 3 activations, the Ising model successfully grouped related atoms without any human supervision or prior labels. It saw straight through the noise of the dilution regime.
Oh, wow.
It gathered the scattered temperature fragments and rebuilt the temperature axis. It did the exact same thing for the color hue fragments.
It even surfaced novel continuous structures, right? Things researchers hadn't specifically prompted for. By analyzing these Ising communities, the authors surfaced a manifold encoding epistemic uncertainty in scientific contexts.
Which is a huge deal. The LLM had internally mapped out a continuous geometric curve representing the degree of certainty or uncertainty in scientific text, and the statistical physics approach mathematically extracted that curve from the fragmented SAE outputs.
That's a major insight into how language models evaluate truth.
It really is. However, and this is a big however, any researcher looking to implement this Ising model approach in their own pipeline needs to be aware of the fundamental limitations here.
Right, I was going to ask, how reliable is this for everyday AI researchers?
The authors explicitly state that this is a post hoc workaround. It's not a cure for the underlying disease.
Because the Ising model is still operating on the diluted fragments provided by the SAE. It can group the overlapping bath mats together, but it can't magically turn them into the perfect, clean X, Y, and Z axes of compact capture.
Precisely. The mixed selectivity is already baked into the features. The Ising model groups them, but the signal remains muddled by the poor initial tiling. If the SAE's internal representation is too severely fragmented, statistical mechanics cannot fully untangle the spurious correlations.
So to achieve true interpretability, we have to move beyond post hoc fixes.
We need new futurizers entirely. We need architectures designed from the ground up to recognize and map geometric objects like curves, tori, Mobius strips as the primitive units of computation.
We have to stop forcing a linear mathematical framework onto a space that is demonstrably nonlinear.
Exactly. The entire field has optimized for sparsity and orthogonal dictionaries because they are mathematically tractable. But the data generated by neural networks clearly follows a totally different set of topological rules. Until we develop interpretability tools that are native to that curved space, we will continually be fighting against the artifacts generated by our own linear projections.
Let's synthesize the broader implications here for you as we wrap up this deep dive. The models we're building are naturally organizing complex human concepts, time, temperature, ideology, uncertainty, into elegant, low-dimensional geometric manifolds. And our current lenses, like sparse autoencoders, are effectively shattering those manifolds into redundant localized fragments.
Yeah.
While techniques like the Ising Model offer a brilliant way to infer the original shapes mathematically, they really highlight the urgent need for a paradigm shift in machine interpretability.
Absolutely.
But there is a final provocative thought I want to leave you with today. We've seen that an LLM can use a torus or a continuous curve to process human concepts like days of the week or color hues.
Yeah.
These models are processing billions of parameters of data, synthesizing patterns that human brains cannot naturally perceive. If an AI uses a continuous topology to understand basic human language, what unimaginable hyperdimensional alien geometries is it forming to represent concepts that humans don't even have words for?
That's a wild thought.
Are we hitting the limits of human geometry and trying to interpret alien machine cognition? Something for you to ponder the next time you are analyzing a cluster of mixed selectivity features. Thank you for joining us for this deep dive on AI Paper Podcasts. We will see you next time.